Okay, so hello again, everybody, and thank you for being here for the presentation about knowledge graphs and analogical reasoning. We've started an example of zero-shot knowledge graph bootstrapping to perspectives about interactions between knowledge graphs and this specific form of reasoning. So this work has been carried out under the 82TA project, which is a national French research project dedicated to analogical reasoning. It is based on 2 publications, so if you want to have more details, you can read the papers or just ask me, and I will be very glad to talk to you about these works. So first, a bit of context. And as usual, a definition of knowledge graphs. No, I'm just joking around, but I'm going to say just a few words. So in this work, we are considering knowledge graphs as directed and labeled multigraphs with different types of nodes, so individuals of the domains, such as Alice or Bob, classes, so types of individuals, writer, painter, which can be hierarchically organized. For example, writer is a class of person and so on. And edges, which are defined by predicates, which allows to qualify the nature of the relationship holding between nodes. So these graphs are represented using logical formalism, which allows to have access to deductive reasoning. So for example, we know that Alice is a writer, and that writer is a subclass of person, and by deduction, we can add that Alice is a person also. So this is one type of reasoning which is associated with knowledge graphs. But what about other types of reasoning? So there are several tasks associated with knowledge graph. The first one being that with an increasing volume of available data in various formats like databases, text, tables, other graphs, we can automatically extract knowledge from such sources to build knowledge graphs. Once knowledge graphs are built, and we know that they are more and more available, they are never complete or never perfect, because knowledge extraction approaches are not perfect. So we need some completion and correction methods, or we need also to align similar knowledge graphs to detect some overlaps. So we have other tasks that are matching or link prediction. We can mine knowledge graphs to discover new and useful knowledge because they are getting bigger and containing additional knowledge units. And finally, we can use knowledge graphs to support various downstream applications such as search, question answering, recommendation, or explainable AI. Throughout all these tasks, we have some issues to face, like heterogeneity issues, vocabularies, different granularity of representation, scalability issues of managing bigger and bigger assets. And as I hinted earlier, we can also study interactions between the deductive reasoning, which is allowed by the logical formalism underlying knowledge graphs, with other forms of intelligent processing. And this is the core of this presentation, where the other form of intelligent processing is the analogical reasoning. And so what is analogical reasoning? So let's take an example. And if I say to all of you, Paris is to France as Berlin is to something, what is the something? And it's of course Germany, because we have here 4 entities, and we have Paris is to France, underlying assumption the capital of France, as Berlin is to Germany, underlying the capital of Germany. So analogical reasoning relies on such proportions based on 4 elements, and the main intuition is to say that A is to B as C is to D, and considering the similarities and the dissimilarities between the pairs of objects. So the similarities and dissimilarities between Paris and France, and the similarity and dissimilarity between Berlin and Germany. So here I manipulated some examples of the real world based on entities, but we can use analogical reasoning for other and more complex objects. For example, and I did not choose this example, pictures. So for example, here, working with images, you can say that the first image is to the second as the third is to the fourth being, for example, in black and white. Here I don't have glasses, I have glasses over there, so we can also add glasses to generate the 4th picture. Other more complex objects are manipulated by analogical reasoning, for example, pedagogical explanations. Electrons are to atoms what planets are to the solar system, so elements that gravitate around one big element at the center. Analogical reasoning is connected with some key cognitive processes: abstraction, inference, creativity. And we have several tasks. So the first one being detecting or mining analogies. Given 4 elements, do they constitute a valid analogy? Or solving analogies, which is given 3-1, predict the last one. The reasoning and integration of analogical reasoning clearly depends on the concrete application of machine learning and AI tasks, but it has been a bit studied, for example, in natural language processing. So how do you compute analogies? So there are some usual examples that are geometric proportion based on multiplication. And you have also the arithmetic proportion, which is based on the parallelogram rule inside one vector space. You can detect analogies using axiomatic, using properties between the objects, using relation between the object, which is somehow similar to knowledge graphs. So wine is to France as beer is to Germany, the underlying relation being the beverage of the country. You can also have functional representation of analogies. So for example, transforming a verb to the past tense. And you have more complex model theoric representation of analogies. So now let's move back to knowledge graphs. We've seen that the task of knowledge graphs are construction, matching, refinement, usage, and various methods have been proposed to tackle these tasks. And lately, we have seen an impressive performance of knowledge graphs embeddings, which basically consists in transforming graph structures into vectors in a d-dimensional space that preserve as much as possible the properties of the graph. And there are various types of model, translational ones, convolutional ones, complex ones, and so on. So as I said, analogies have been extensively studied in natural language processing for tasks such as morphology and so on. And recent models have achieved high performance using word and character embeddings. And so one intuition is, can we do the same with graph embedding models, especially given that some models can be intuitively related to analogies? So for example, the translational model trans-E basically validates the parallelogram rule of analogical reasoning, because France is to Paris, as Sweden is to Stockholm. And so we have here the parallelogram of analogical reasoning basically ensured by the model. Few works have studied analogical inference. Is this desirable for KG refinement? Can we use a model for link prediction or data mining to validate analogical word analogies or so on? And basically the answer is yes, but it's very, they are the first few works about that. And so the main questions of our work was, can we do more? Can we use analogical reasoning into other KG related tasks? And how can we integrate analogical reasoning with, for example, graph embeddings? And the first example we carried out was the example of KG bootstrapping. So to introduce what is KG bootstrapping, let's consider the virtuous loop of knowledge extraction. When you want to complete a knowledge graph, you can extract knowledge from text and tables with knowledge extraction approaches, which relies on terms and relations coming from the knowledge graph, which is great because they can be used to focus the knowledge extraction approaches onto terms and relations of interest. A problem arises when your knowledge graph is empty. So you don't have terms and relations to focus on, and so you cannot perform close knowledge extraction approaches. So how can you bootstrap the knowledge graph? How can you start this process to then ensure the virtuous loop? First, let's talk about open information extraction. In some contexts, you may not want to do that because you will have to ensure some quality process at the end to remove duplicates, ensure a high quality nucleus of the knowledge graph. So it's mainly not adapted, or you may need some experts or quality process afterwards. So this is not the good idea that we wanted to use to bootstrap a high quality core nucleus. In the principle of the linked open data, the idea is to be able to reuse available data. So why not use a generic knowledge graph available like Wikidata? This is a good idea because of the genericity of Wikidata, you will have various types of knowledge and including some knowledge of interest for you. However, you will have to manage more than 106 million of entities and billion of edges, which of course pose problems of scalability. And you will have knowledge about various domains. Some of them may not be of interest to you. And so you will have knowledge extraction approaches that may focus on terms and relations that do not interest your use case. So Wikidata is not the answer, but maybe you can just select subgraphs of interest to focus on specific domains of interest from Wikidata. So how can you do that? Well, maybe you have a set of entities of interests that can be used, that can be extracted from company vocabularies, glossaries that can exist inside your company, or maybe inside the texts of your company, and having just experts review that a bit, map them to Wikidata, and have sets of entities of interest, so in yellow. And then you can browse the ontology hierarchy of Wikidata to retrieve the subclasses, the superclasses, and the subclasses. So we were not the first one to propose this approach. The first one dates back to 1996. But nobody has actually evaluated the process. Is what you get of good quality or not by just selecting subgraphs like that? And it still poses some scalability issues because of the size, the sheer size of Wikidata. Just getting the subclass leads you to have more than 1 million of entities from only 800 seed entities. So this is very huge, especially if you have a small proof of concept or a small knowledge graphs that you want to manage on your servers. So okay, we can select subgraphs like that, but maybe we need to prune somehow. And this is true, especially because of the modeling, the collaborative modeling of Wikidata. You may encounter entities that are not of interest to your use case. So let's take an example. Let's start from Microsoft SharePoint and browse the hierarchy. I think a focus of IT computer science domain. So Microsoft SharePoint, you can go to social software, which is of interest. And then browsing downward, you can have file sharing software, which is still of interest for IT computer science stuff. And you can also have dating app, and you'll start to figure out that the knowledge is drifting and you don't want dating app. So you have to prune somehow again, because just browsing the hierarchy is not good enough to have some specific focus terms. So again, we were not the first one to investigate this issue. The first one being Square2 in 1996, but performing manual pruning. So basically, they selected entities of interest, and experts reviewed the graphs, the subgraphs to select or not. Other approaches tried to do the same, but with specific focus. For example, Bordea tried to rebuild an ontology, selecting leaves and root. Here, we don't want to do that. We just want to select an entities and browse the upward and downward hierarchy. And with Luca, which was an intern at the time, we also proposed some threshold method based on knot degrees and distance in the embedding space. But it was not enough, and it was not clearly evaluated. So could we do more? And that's what we propose. By using analogical reasoning and getting a list of seed entities, the Wikidata knowledge graph, and expanding and pruning within this knowledge graph to bootstrap our own knowledge graph. Using a zero-shot analogical pruning model and providing 2 data sets, which we were the first one to provide, to clearly evaluate the task and the performance of models. So how can we use analogies to perform KG bootstrapping and to select entities of interest? So from a seed entity, for example, Microsoft SharePoint, I want to be able to browse the hierarchy And on each reached entity, for example, social software, I want a model to output 1 if the reached entity should be kept, or 0 if the reached entity should be pruned. And if it is kept, I can then browse its neighbor, or if it is pruned, I just stop the traversal here. Using analogies, what I need is examples of seed entities and reached entities for which I know the decision, for example, keeping or pruning, and then put some seed entities and reached entity for which I don't know the decision. And if I ask my analogical model, is this an analogy? And the model says yes, then I know that I can extrapolate the decision on the left to the decision on the right. So if on the left, I know that I should keep the entity, and the model says this is a valid analogy, then I should also keep the entity on the right because this is a valid analogy, so the same decision should apply on the left and on the right. So let's take an example. If I know that from MPEG 4, I have kept multimedia format, and from SharePoint, I don't know if I should keep file sharing software or not. If the model says this is a valid analogy, then knowing that I kept multimedia format, I should also keep file sharing software. So we also proposed another model where on the right, instead of just one reached entity, we have the path leading to the reached entity to have just a bit more context in the graph. And that means that from experts, we only need seed entities, which can be automatically extracted from texts of the company or from text of interest. And we need few people to annotate examples of seed entities and reached entities of interest. So this is a simple model, and it's implemented actually with a convolutional model applied on embeddings. So we have embeddings of entities, graph embeddings of entities, and we have convolutional layer. The first one computing the similarity and dissimilarity between AB and CD, and the second layer comparing the vector of similarities and dissimilarities, followed by a flattening and a sigmoid function to have a classification output of 1, a valid analogy, or 0, an invalid one. Okay, so now we have to experiment. So let's consider 2 data sets that we built by hand with my PhD student Luca. The first one being focused on computer science IT terms, and the second one being focused on broad topics like food, sports, academic, and so on. And let's compare some models. First, let's use a basic one, just having a threshold of depth considered in the hierarchy of Wikidata. What we can see is we have some good recall, but we have a very bad precision. Of course, because the terms in Wikidata are collaboratively edited from different communities, and different communities may have different granularity of representation. So one depth in the hierarchy may not be the same in one domains from the others. So having just a global threshold doesn't work. And now let's compare the 2 best performing systems, which are LSTM and our own path analogy. What we can see is our path analogy is actually very competitive compared with LSTM, especially on the second data sets, where we can have some improvements of 4 points on accuracy or 2 points on F1 score. So it's quite good. It's quite good, but it's still close. However, we can do the same performance or better with 800 fewer parameters. So LSTM is basically 210,000 parameters to learn, where we only have 104,000 or just 200 parameters. So we are here with an example that analogical reasoning allows a very frugal learning with few parameters to have a very good performance. And now let's try some extrapolation experiments, because analogical reasoning is supposed to allow to extrapolate. and humans use it every day for extrapolations. So let's train our models on dataset 1 and test them on dataset 2. And we can see that on that, we have a close precision and 9 points of difference on recall, 5 points on F1 score, and 4 points on accuracy. So clearly, the model is able to outperform LSTM with fewer parameters, and especially on generalization capabilities. So this shows that analogical reasoning is a very interesting form of reasoning and provides some interesting properties, frugality, generability on some interesting tasks. So can we do more? Can we use analogical reasoning on other tasks of the KG lifecycle? Well, yes. Let's take some example, if I still have the time, yes. So first, let's consider a semantic table interpretation, which is the process of annotating the table with elements of the knowledge graph to be able to extract knowledge from table and complete knowledge graph, or the other way around, or just understand the structure of table. So STI is based on 3 subtasks. The first one being cell entity annotation, that is to annotate each cell with the entity of the knowledge graph. Column type annotation, which aims at associating columns with the type of the knowledge graphs. For example, the column country is basically annotated with the country class. And columns property annotation, which associates pairs of columns with some properties. For example, between the country column and the capital column, we expect the property capital of to be represented. So interpreting tables is a difficult task compared to classical NLP tasks because, of course, we have some different encoding char sets, but we have also misaligned cells, missing values, and especially very little context to disambiguate entities. So for example, the Germany entity over there, just based on the label, could be annotated with one entity from Wikidata, which is a European country, but also another entity from Wikidata, which has the exact same label, Germany, but is a constituency of the European Parliament. So totally different stuff. But there is a useful property, especially in this type of table. There is a semantic coherence inside columns. So I only have country in the first, cities in the second, languages in the third, and GDP in the fourth. This only works because this table is an horizontal one that I have to read line by line. Other types of table raise additional challenges. And I can see columns as analogies, actually. I can build lots of analogies, being France is to Paris as Germany is to Berlin, France is to Sweden as France is to Paris as Sweden is to Stockholm, and then France is to Paris as Finland is to something I need to predict to fill the missing values. So I can do that by analogy solving and retrieving entities from the KG or generated one. And to disambiguate, I can choose the entities that maximizes the analogy detection task. So this is one example of using analogies. Of course, you have some scalability issues because I can generate lots of pairs of columns. And so, for example, just from country and capital, I can already generate 12 analogies with only a 5-line table. So let's consider that for big CSV or big tables available on the internet. Of course, this works for horizontal table where I have a semantic coherence for each column. This is not always the case. Some tables are matrices, some tables are vertical, and so each time I have to adapt the analogical view of the table. I can also use analogical reasoning on other tasks, for example, the matching task. If I consider 2 knowledge graphs and I want to identify the overlapping entity, can I again use analogical reasoning? Well, yes, from 2 points of view. For example, if I know that Paris in the first knowledge graph is aligned with Paris in the second knowledge graph, can I predict what France in the French knowledge graph should be aligned to in the second? So I have a first analogy over there. And I can use other existing alignments to predict new ones. I still have the same problem about scalability, because if I have many alignments existing, I can use all of them to predict entities in the second part of the analogies. I can have another view, which is to say that Paris in K1 is to France in K1, what Paris in K2 should be to something, which then should be aligned to the France in K1. So this is the second formalisms. Which one is the best? Well, for now, it's up to be tested and experimented, because this was just a formalization. So again, you have lots of challenges to overcome: mix of entities and literals, completeness, sufficient overlaps, how many existing alignments do you need to have a good performance, and so on. So to sum up, we've seen that analogical reasoning gave us some interesting properties like generalization, frugality, and allows to have a good performance on knowledge graph bootstrapping and knowledge graph pruning. However, lots of questions are still open. So how can we apply that on other knowledge graph related tasks? For example, matching, semantic table interpretation, but one could also think of link prediction and so on. Is this scalable? How do I choose my analogies? So for example, I predicted that SharePoint aside file sharing software should be kept from SharePoint based on MPEG-4 and multimedia format. But was the pair I chose on the left competent for this classification? Or can I choose other entities? And if I choose other entities, on which criteria? And because I have analogy that can be read by humans, somehow they give me an explanation of what the model is doing. So if I say this is a valid analogy, this means that I kept file sharing software because this is to SharePoint, what multimedia format is to MPEG-4. Can I use this kind of readable analogies for explainable AI and to give that to humans for them to understand what the model is actually doing? So these are actually open questions that we will explore in the next step of the AT2TA project. So that's it for my talk, and thank you very much.
Thank you very much.